want to solve this week is as follows. We want to find all the functions f with the following property. Let's make sure we understand all this notation. First of all, let's recall that R stands for the real numbers. Here are some examples of real numbers. Real numbers can be ratios like 1/2 or -5/2. They can be integers like -1, 0, 1, 2, 10, -5, etc. They can be irrational numbers like the -square root of 2 or e or pi. On the other hand, the square root of -1, which we usually denote as I, is an imaginary number. It's not a real number. Or 5 minus 2i, that's a complex number, not a real number. Next, when we write this symbol, we say f maps the real numbers into the real numbers. For example, consider the function f of x is x squared. This function maps the real numbers into the real numbers. You plug a real number in, like -2, and you get a real number out, like 4. Another nice example is the cube function, and that one looks like this. So here is the function f of x is x cubed. This function also maps the real numbers into the real numbers. For example, this time when you plug in the real number -2, the output is the real number -8. Finally, when we write this symbol, we say the numbers x and y are in the set of real numbers. So, the problem of the week asks that we find every function f that maps the real numbers into the real numbers that satisfies the following property for every pair of real numbers x and y. So we need that f evaluated at x times f at x plus f at y needs to be equal to the square of f at x plus y. And this needs to be true for every pair of real numbers x and y. Before we start solving this problem, let's review one more concept which will arise within the solution, and that is the concept of inverse functions. Suppose we are given two functions, f, which maps its domain x into its codomain y, and g, which maps y into x, then f and g are called inverse functions, provided that both of the following are true. First, if we plug y into g and then take that result and plug it into f, we get y back for every y in the domain of g. And second, if we plug x into f and then take that result and plug it into g, we get x back for every x in the domain of f. So the idea of inverse functions is that they undo each other. So when you compose the two inverse functions, you always get back the same argument that you plugged in. In particular, if x and y are both the same and both equal to the set of real numbers, then this definition of inverse functions simplifies as follows. We just need that f at g at x is x, and g at f at x is also x, for every real number x. And the geometrical interpretation is that the inverse function g is obtained from the function f by reflecting the graph of f across the line y equals x. Let's look at a couple of familiar examples. For example, let's again consider the function x cubed, which maps the real numbers into the reals. And when we reverse the roles of the x and the y axes and reflect this graph across the line y equals x, like this, we see that we get another function, the cube root function. G of x is the cube root of x, which maps the reals into the reals. And by definition, these are inverse functions because for every real number x, plugging g at x into f gives us x back, and plugging f at x into g also gives us x back in this way. For example, if I plug in -8 into g, I get -2, and then if I put -2 into f, I get -8 back, and so on. This is true for every real value x. As another example, let's again consider the function x squared, which is a function that maps the reals into the reals. This time, when we reflect the graph of f across the line y equals x and interchange the role of the x and the y axes, this time we don't get a function because we can get a vertical line that intersects this resulting graph more than once. So this reflection is not a function. If we restrict the domain of f, then we can make it invertible. For example, let's consider only the right-hand side of this graph, like this. So this is the x squared function, but this time f maps the non-negative real numbers to the non-negative real numbers. So when we take the right-hand side of the x squared function and reflect it across the line y equals x, like this time we do get a function, the square root function. So the right-hand side of f, when we restrict f in this way, does have an inverse function, namely g is the square root of x, where g maps the non-negative reals into the non-negative reals. And we can see by the definition that f and g are inverse functions because for every non-negative real number x, f evaluated at g of x is x, and g evaluated at f at x is also x. For example, when I plug 4 into g, I get 2, and then when I plug 2 into f, I get 4 back. One final remark about inverse functions. Let's be clear about the following distinction. because there are two different kinds of inverse which often get confused: the multiplicative inverse and function inverse. The multiplicative inverse is one when I take the inverse of a number. For example, the inverse of 3 is 1 over 3. It's that number that when I multiply it by 3, I get 1. And function inverse is composition inverse. So it's the inverse that when you do function composition, you get x back. So function inverse is not the same as multiplicative inverse. So if f of x is the square root of x, its inverse function is x squared. We would not write 1 over the square root of x. That's not the same thing at all. So except for the function 1 over x, function inverse is never achieved by taking the reciprocal, as you would in the multiplicative inverse. Function inverse is found by interchanging the role of x and y. Now that we've reviewed the concept of inverse functions, we're ready to solve the problem. This took me about 10 steps, which I'm going to outline as follows. So I'm searching for the kind of function f that satisfies this condition for every real value x and y. I need to extract some information about the shape and behavior of f from this property. One of the easiest questions I could ask is, where does 0 go? What's f at 0? I'll call it a. I'll give it a name. Also, I could ask, is there anything that maps to 0? So what number can I plug into f to get 0? So if I can't visualize anything about the shape or behavior of a function that maps the reals to the reals, 0 is often a really good place to start. Other easy real numbers to try are 1 and -1. So that's why for step 1, I decided to plug in 0 for x right here and just find out what happens. So according to this formula, when x is 0, we get f evaluated at 0 times f at 0 plus f at y on the left-hand side, and on the right-hand side we get the square of f at 0 plus y. And this is true for every real number y. Here I'm using the upside down capital A, which means for every, or for all. Simplifying this expression down, we have 0 here, so we have f evaluated at f at y on the left-hand side, and on the right-hand side we have f evaluated at 0 squared plus y, but so I don't have to write so much, I've decided to give f at 0 a name. I'm calling it a, just for convenience. So by plugging in 0 for x into this expression, I've discovered that f evaluated at f of y is a squared plus y for every real number y. I'm going to write that down on my list. I'm keeping track of all the results that I've come up with at each step of the way. So far, I've given f at 0 a name. I'm calling it a, and I know that for every real number y, f evaluated at f at y is a squared plus y. What about my second question on my list? Is there a number that maps to 0? Looking here, I see I could do it. If I could set y equal to minus a squared here, this would become f at y is the number that I would plug into f to get 0. So that's what I'm going to do in step 2, like this. So from step 1, I know that f evaluated at f at y is a squared plus y for every real number y. Setting y equal to negative of a squared in this expression, we get f evaluated at f at negative a squared is a squared plus negative a squared, which is 0. So the thing that I plug into f here to get 0 is f evaluated at negative a squared. I'm going to call it b. So f at this value of b is 0, where b is f evaluated at negative a squared, where a is f at 0. I'll add that to my list of conclusions here. So I have, there is a b that gets mapped to 0, namely b is equal to f evaluated at negative a squared, where a is f at 0. So far, I don't know what the values of a and b are, so that's a question. I wonder what a equals, and I wonder what b equals. I think I'm going to try plugging b in for x next, because f at b is 0, so that will simplify this expression quite a bit, because this will become 0 in this expression. And let's see if I can get some more information. So that will be my next step, like this. So recall, b is the number that when I plug it into f, I get 0, and I'm going to take b and plug it in for x in the condition that's stipulated in the problem. So remember, the problem says that this condition must be true for every x and y in the real numbers. So I'm going to replace x with b, and we're going to get f at b times f at b plus f at y for the left-hand side. And we're going to get the square of f at b plus y on the right-hand side. And this must be true for every real number y. But f at b is 0, and so the left-hand side simplifies to f evaluated at f at y, and the right-hand side simplifies to just y. Wow, that tells us two things. First off, we've just discovered that f is its own inverse function, because f evaluated at f at y is y for every real number y. And also, combining this result with step 1, we've just discovered that a must equal 0. So writing down in my list of conclusions, we've just discovered that f is its own inverse function, and furthermore, because f evaluated at f of y is both y and a squared plus y for every real number y, it must follow that a is 0. I'll write that result down in detail in step 4. So I'll write each step down just to make sure I'm being clear. So step 4, here's my list of conclusions so far. And from steps 1 through 3, I know that f evaluated at f at y is a squared plus y for every y on the one hand, but at the end of step 3, I got that f at y is y for every y. And so since y must equal a squared plus y for every real a, then it follows that a squared must equal 0 by subtracting y from both sides of this equation. And so of course it follows that a equals 0. And what about the value of b? Well, b is f at minus a squared, so we have b is f evaluated at minus a squared, but a is 0, so b is f evaluated at 0, but f evaluated at 0 is a, but a is 0, so b is 0. And so now we know that f evaluated at 0 is 0. For any function that obeys this property for all real x and y. So what I know about the graph of f so far is that f is its own inverse. Graphically, that means that f is a reflection of itself across the line y equals x, and we know that the graph of f goes through the origin. F evaluated at 0 is 0. Let's play around with this condition some more. So far I've plugged in 0 for x. I wonder what happens if I plug 0 in for y. So that's what I'm going to do in step 5, like this. So again, the condition stipulated in the problem is that f has to obey this property for every real x and y in R. So I'm going to try substituting 0 for y in this expression, and let's see what happens. So the left-hand side becomes f evaluated at x times f at x plus f at 0, and the right-hand side becomes the square of f at x plus 0, and this must be true for every real value x. Again, this comes from substituting in 0 for y in this expression, but we know that f at 0 is 0, and so the left-hand side simplifies just to f evaluated at x times f at x, and the right-hand side simplifies down to just the square of f at x. And this equality must hold for every real value x. I'll write that down in my list of conclusions. So at the end of step 5, I've discovered that f evaluated at x times f at x is the square of f at x for every real value x. So I could combine this thought with this property, which we got at the end of step 3. Substituting x for y here, we know that x is f evaluated at f at x. So I could replace x here with f evaluated at f at x. And then let's see what this expression looks like when we do that. So I'm going to do that in step 6, like this. So for step 6, first I write down what I had at the end of step 5, which says f evaluated at x times f at x is the square of f at x for every x in the real numbers, but I can combine this result with what I know from step 3, replace y with x here, so we know that x is f at x because f is its own inverse. So here I can replace x with f at x in this expression here. And this must be true for every x in the real numbers. But wait a minute, this expression looks just like this expression. If we just switch these around, like this, so here, I'm just rewriting this same expression. I haven't changed it. I'm just multiplying these in a different order. So this expression is f evaluated at the product f of x times f evaluated at f at x. But this expression looks just like this expression, which we know must be true for every x in the real numbers. And if we replace x everywhere here with f at x, we get this expression. So since this must be true for every real x, it's true if I replace x with f at x. So this expression becomes f evaluated at f at x times f at x, and the right-hand side becomes f at x, quantity squared. But we know f is its own inverse, so we know that this quantity inside the square, f at x, is just x. So now we know that this quantity, which is equal to this quantity, is equal to the square of x, and at the same time, it's equal to the square of f at x. And that means that f at x must equal plus or minus x for every real x, like this. So because this expression is the same as this expression, and this expression equals the square of f at x, and this expression equals x squared, we have discovered that the square of f at x is the square of x for every x in the real numbers. Solving for f, we know that f is either plus or minus x for every real x value. So I'll write that in my list of conclusions. We know that for every real x value, f at x is either plus x or minus x, and we also know that f is its own inverse, and so that f is a reflection of itself across the line y equals x. So what kind of a function is f? Well, there are three possibilities. So, if f at x is either plus x or minus x for every x in the real numbers, there are three possibilities. The function f could just be f of x is x, or f at x could be minus x, or f could be a combination thereof. F could be x some of the time and minus x some of the time, just so long as its graph is symmetric across the line y equals x, so that f is its own inverse. So these are the possibilities for the function f that must satisfy this condition for every pair of real numbers x and y. These are the only three possibilities. F could be the function y is x, or y is minus x, or some combination thereof that's symmetric across the line y equals x. So let's check each of these possibilities and see if each of these functions satisfies this condition. I've decided I'm going to look at the last possibility first because it looks like the most complicated part to check. So I want to know if a function like this could satisfy this condition. So I'm going to consider this possibility in step 8 like this. So for step 8, I want to know, does a function like this satisfy the condition that's stipulated in the problem for every pair of real numbers x and y? So I want to know, can we have the following? Can I have a function which is x part of the time and minus x part of the time and symmetric across the line y equals x, such that it satisfies this condition? So we have a non-zero v which maps to minus v, and we have a non-zero value of w which maps to w. Well, if f satisfies this condition and this condition, we can plug v and w in for x and y like this and find out what happens. So I plugged in v for x and w for y, and I got f evaluated at v times f at v plus f at w is equal to the square of f of v plus w, but we know that f at v is minus v, so v times f at v is minus v squared, and we know that f at w is w, so the left-hand side becomes like this, and since f at v is minus v, when we square it, we get v squared, and so the right-hand side simplifies to v squared plus w. So this says that this function f satisfies that f evaluated at minus v squared plus w must equal v squared plus w. But on the other hand, I think we got a problem because we know that f at x is either plus x or minus x for any x you plug in. So when we plug this value into f, we must get either minus v squared plus w or v squared minus w. And this is not what we're getting. So looking at that in detail, we find, so the end of step 6 tells us that f evaluated at x is either plus x or minus x, no matter what real number x we plug into f. And so replacing x in this expression with minus v squared plus w, that means that f evaluated at minus v squared plus w is either the plus of this, so minus v squared plus w, or the minus of this, so v squared minus w. So those are our two options. But at the same time, because we're satisfying this stipulation that was given to us in the problem, we know that f at minus v squared plus w is equal to this. And these don't match up. This option tells us that f at minus v squared plus w must equal minus v squared plus w, and simultaneously it must equal v squared plus w. That says that 2v squared is 0 or v is 0, which is a contradiction because we specified that the v and the w in our graph are not 0. And likewise, this option, if f at minus v squared plus w is v squared minus w, and simultaneously equal to this, then we have v squared minus w equals v squared plus w. Solving, we have 2w equals 0, so w is 0, which again is a contradiction because we specified that w is a non-zero number. So in either case, we get a contradiction. So it's not possible for a function like this, which is a combination of x and minus x, to satisfy both the condition of the problem and the fact that f at x is supposed to equal plus or minus x for every x. Not possible. So in step 8, we've ruled out this possibility. And there are only two possibilities left. Either our function is equal to x or minus x. And so in steps 9 and 10, I'll check if these functions each satisfy the condition of the problem. And if so, these are the only functions that can satisfy the condition of the problem. And so I'm going to check these last two functions like this. So at the end of step 8, we've discovered that there are only two possible functions which could satisfy the condition given in the problem. So in step 9, I'm going to check the first of these possibilities, the function f at x is x. Okay, let's plug f at x is x into this condition, and let's find out what happens. Does f evaluated at x times f at x plus f at y equal the square of f at x plus y for all real x and y? Well, f at x is x, so the left-hand side becomes f evaluated at x times x, which is x squared, plus f at y, which is y, and the right-hand side becomes f at x is x, so this is x squared plus y. So we're asking, does f at x squared plus y equal x squared plus y? And yes, it does. Because whatever you plug into f, you get it back. So f evaluated at x squared plus y is x squared plus y. So yes, the left-hand side is equal to the right-hand side for every pair of real numbers, x and y. So yes, the first possibility, the function f at x is x, does satisfy the condition given in the problem. And finally, step 10, what about the function f at x is minus x? And that goes like this. So for step 10, we want to know if the function f at x is minus x satisfies the condition of the problem. Well, we know that whatever we plug into f, we get the negative of that result. So the left-hand side becomes f at x is minus x, so x times minus x is minus x squared. When I plug y into f, I get minus y, and we want to know, is that equal to the right-hand side? When I plug in x into f, I get minus x, and so we want to know if this equals the right-hand side, which is the quantity minus x squared plus y, for every pair of real values, x and y. Well, again, What does f do to any number you plug in? It takes the negative of it. So f evaluated at negative x squared minus y is the negative of negative x squared minus y, or positive x squared plus y. And the right-hand side, the square of a negative just becomes positive, so the right-hand side becomes x squared plus y. And so yes, the left-hand side and the right-hand side both equal x squared plus y for every pair of real numbers x and y. And so yes, the function f at x is minus x satisfies the condition given in the problem. And so now we've discovered that x and minus x are the only two functions that satisfy the condition given in the problem. Because recall, at the end of step 7, we had only 3 possibilities. In step 8, we ruled out this possibility, so the only 2 possibilities that remain are x and minus x, and in steps 9 and 10, we verified that x and minus x do satisfy the condition of the problem. So the conclusion is that there are only 2 functions f that map R into R, such that this condition holds for every pair of real values x and y, and those 2 functions are f at x is x and f at x is minus x. And the problem is solved.